Okay, so we're going to start by going through minimal automata. This was one of the topics which some people voted for. So in terms of minimal automata, there's several automata that can recognize the same language. And to say a DFA is minimal, it has these two properties. So every single state in that DFA is reachable. So there's always a path from the initial state to X, meaning we can't have something like, this is our initial state, this might go here, this might go here, this might go here. We can't have something like this because this state here is unreachable. So this wouldn't be a minimal automata. And then the second condition is that any two distinct states, X and Y, in our DFA are not equivalent. So no two states are equivalent. And this means there's a word that X accepts, that leads from X to an accepting state, but Y rejects, or vice versa. I just want to explain this definition in more detail because I don't think we covered it a lot. So when we say a state accepts a word, so usually we talk about a DFA accepting a word, but when we talk about a state accepting a word, that just means from that state, if we then read that word, starting from that state as the initial state, we end up on an accept state. So, for example, our initial state will accept AA, because that will just take us down here and then down here. But we can also say state 2 will accept BAA, because we can do this, this, and this. So from state 2, if we read BAA in, we'll end up on an accept state. I've just got some questions here, if you guys want to have a go at this. Just drop your answers in chat. Yep, I'm recording, Kevin. Oh, good. But yeah, just have a go at these. Do this in Kahoot. I have not set up a Kahoot. Maybe next time. Right, Fred has posted some answers. Okay, let's see. So, does 1 accept A? If we take an A here, we go to 2. So 1 does accept A. No, sorry. No, 2 is not an accept state, so 1 does not accept A. Yeah, you guys are right. Okay, so 1 does not accept A. Does 2 accept ABA? ABA. We end on an accept state. So, yep, 2 accepts ABA. Does 1 accept ABA? ABA. We end on 2. That is not an accept state. Does 3 accept ABABB? So from 3, A, B, A, B, B. We end up on 3. So it does, in fact, accept that string. And then finally, does 3 accept the empty string? If we're at 3 and we don't consume any characters, we just accept. Cool. So usually when we say a DFA accepts a word, then we'd start at the initial state. But when we're talking about whether a state accepts a word or not, we're talking about if we consume that word starting at that state, then does it lead to an accept or reject state? Okay, just wanted to get that terminology cleared up. Okay, so building on that, this second point is equivalent to saying that the two automata that we obtain from the original one by changing the initial state to X and Y, respectively, are not language equivalent. So changing that initial state and tracing through it in that way. Okay, so for example, this DFA is minimal because no two states are equivalent. So to go about proving this, you want to look at every possible combination of states. We know 2 isn't equivalent to any of the states because this is the only one that just accepts an empty string. This is an accept state. We know that 7 and 95 are not equivalent because 7 accepts C, whereas 95 does not. 3 does not accept C, and 18 does not accept C. So 7's the only one that accepts C. So this is unique. This is unique. And then this one accepts B, this one doesn't, and this one doesn't. So this is unique. And now we just need to find how these two are unique. So for example, 18 doesn't accept anything, whereas 95 accepts A. So this accepts something that this doesn't. And so all of these states are unique in some way. And we've just written this out as 5 bullet points. Can we say 7 is unique because it's an initial state? Not exactly, because when we're talking about it being equivalent to another state, we're just talking about what it accepts. So if we had something like 7, or say we had another state called 4, 4 took AB to go here, and 4 took C to go here, these two would be equivalent because they both accept the same words. So 7 wouldn't be unique in this case, just because this 4 is the exact same as this 7 in terms of what words it accepts and rejects. Does that make sense? Hope that's clear. Cool. Okay. So any automaton which is not minimal can be reduced to a small automaton by either removing unreachable states or collapsing equivalent states. So we can collapse 2 or more equivalent states by following this procedure. We choose one of the states we want to keep. Let's call that X, and then one by one we pick every other equivalent state to that and redirect all of the transitions to this new state. So if we had 3 states like this or 4 states like this, previously it might have looked something like this. Okay, how shall we? I think the best way to do this is to look at an example, actually. Okay, quick fact, the minimal automaton accepting a given regular language is unique up to isomorphism. So there's only going to be one sort of structure or shape in which we can represent a minimal automaton. Cool. Okay, I've got an example here. So if we have this DFA here, is this a minimal automata? How can we check? I think, yeah, we got a bit confused there, but we reached the right answer. So 1 is accepting and 2 is not, is the exact reason why this is a minimal automata. So both of these states will accept different words. For example, 1 accepts epsilon, but 2 doesn't accept epsilon. And 2 accepts A, while 1 doesn't accept A. So both of these states are unique, both of them are not equivalent, and so this is minimal. Okay, let's take a look at another one. This is a slightly bigger one. Is this a minimal automata? One sec, let's make this an accepting state. Okay. Is this a minimal automata? Okay, so we've got a message in chat saying no because 5 and 2 are identical. And that's right, so 2 and 5 both accept the exact same words. So if 2 accepts something, like AA, 5 will also accept AA. If 2 accepts a BA, 5 will also accept a BA. So both of these 2 states are equivalent in that sense. So if we want to take our first step to minimizing this, what do we want to do? Okay, we've also got 1 and 4 as identical states, someone's pointed out. Inbound transitions don't matter, no, because we can just redirect all of those inbound transitions to a new state. So when we're thinking about state equivalence, we just care about what it accepts. Yeah, so we want to minimize this. This is not minimal. So we want to minimize it. And so we want to find some states that are equivalent. So our first pair of states that was pointed out is 2 and 5. 2 and 5 are both 2 equivalent states. So 1 and 4, yeah, these are another pair of equivalent states. But looking at these 2 first, so we want to merge this into one state essentially. And so we can have something like this too. All of our original transitions, like this A, can now go to this state. This original transition to 5 can also go to this state. So we redirect everything to this new state. That should be an A. This should be an A. Okay, so now we're going to this new state. And now we can look at the transitions on these states and just copy them. So this A to 3 and this B to 6. So we can get rid of... Oops, got rid of too much there. We can just have A going to 3 and B going to 6. So A goes here, B goes here, and then these 2 are just unreachable because we've got rid of these transitions. And we want to get rid of unreachable states, so we can just delete these 2. So now we've merged those 2 states into this single state. Does that merging process make sense, what we've done there? Do we need to all is 2.5? Cool. Do we need to call it 2.5? I mean, in terms of merging a DFA, we don't really care about the names. We just care about merging equivalent states. But I mean, you can do that to keep track of what you've merged if you want to. We can call this anything though. Marks wise, okay, yeah, maybe to be on the safe side, just write it as what we merged. But yeah, I wouldn't worry too much about that. Okay, so we said that these two are also equivalent. For example, one accepts AB. No, one accepts ABA. 4 accepts ABA. Both of these accept the same thing, because as soon as we consume a B, we just go to each other, and as soon as we then consume an A, they both end up here. So if we have these two states, how would we go about merging these? What transitions would we need to add? 1 for loop B. Okay. Good, yeah, so we want to first make a new state, so let's just call it, we can call it 1, 4, because this is the merging of those two states. Okay, all of the outgoing transitions on 1 and 4 is just this A going to here, and then we also have a B, so the B of 1 goes to 4, and the B of 4 goes to 1, so we can write this as a sort of reflexive arrow, just B, and then we've got rid of this transition, got rid of this transition, and we've put it here. We've got rid of this transition and put it here. So now we can delete these transitions. We can delete these transitions. This would be our new initial state, because 4 was originally our initial state. So we can get rid of this, and this is just a hanging state. We can get rid of that. And now we've merged 1 and 4 into a single state. So now we have something like this. Are any other two states equivalent? No. How do we know which to merge first? It doesn't matter which ones we merge first. We'll always reach the same minimal automaton. Yeah, Fred's correct. So yeah, in an exam, I'd probably just draw out the automata again and again, just to show exactly what it is we're merging. That's probably the best way to. Yeah. Could you show the initial DFA? Yeah, in hindsight, I probably should have. Let me get the initial DFA back. So the initial DFA was. Let's try and reconstruct it. Okay, so we had 4 down here, we had 1, we had this going to 2, I believe, and then we had 5, and then we had 3, and then we had 6. This was an accept state. AB. Yeah, I would control Z, but then we lose all of these steps. Okay, and then this had A going to here, this had A going to here, this had B, this had B, I believe. What are we missing here? Okay, A goes to 2, 5, so we had A going here. I think it was this. Oh, Sid's got it. Okay, lovely. BA, yeah, looks like that's the same. Cool. So yeah, this was our initial DFA, and this is how we've minimized it. Are we sure 3 and 6 is not equivalent? 2, 5, and 6 are the same. So 2, 5 accepts BA, 6 accepts BA, 2, 5 accepts A, and 6 accepts A. So yeah, these two are also equivalent. Can we think of any words which one of these accepts which the other doesn't? No, because 2, 5 accepts A. So does 6. 6 also accepts A. So when we're comparing the state equivalents, we don't actually care about the receiving. We just care about what it accepts and what it rejects. So if we wanted to then merge 2, 5, and 6, we'd create a new state. So something like 2, 5, 6. And so you can't get to 6 using A. We can't get to 6 using A, but that's fine because we just care about what we can accept from there. So when we then merge it, we will be able to get to this new state with A. So if we have something like A here, and then we draw out the transitions we had from both of them previously. So B takes us to 6. So B takes us here, and A takes us here. Then we can get rid of these transitions, get rid of this state here, and we're left with, oh, this B would be this actually. B would be this arrow to 6 because 6 is in that set. So we'd have something like this. Does this seem correct to you guys? So can we think of any words which one of these accepts, which the other doesn't? So, for example, this one will accept BAA, this one accepts BAA, this one will accept ABA, this accepts ABA. So both of these are equivalent, both of these are language equivalent, but the idea is this bottom one is a minimal way of representing that language equivalent language. And I believe I got something similar. Yeah, so this is what I got, where we have 3 states and we just consume in this order. Does that make sense to people in terms of how we've worked out that minimal automata? We've taken 2 states which are equivalent, state equivalent, which means they both accept the same word. We merge them into one state. We put all of the incoming transitions to go to that, and then the outgoing transitions. We've got a question from Danny. Are 1, 4, and 2, 5, 6 equivalent? So this accepts AA, whereas this rejects A. So 1, 4 rejects A, whereas 2, 5, 6 accepts A. So these two aren't in fact state equivalent. Yeah. Cool. Okay, that's everything I wanted to cover on state equivalence. In the initial DFA, if we combine, okay, yeah, let me take a look at this. So we've got a question from Bonbons. If we combine the 1 and 4 before the 2 and 5, wouldn't it be an NFA instead of a DFA because of the A transition? So if we might combine 1 and 4, let's go through this. So we'd have a new state, which is obviously 1, 4. Our outgoing A would go to this 2. Wait. Ooh. Okay, so all of the outgoing transitions. If we sort of merged that 1 and 4 first, we'd have 2 A transitions defined. So one going here and one going here, and that would become an NFA then. And then we'd have our B here, this would be our initial state, and then we'd get rid of this. But I don't know if that's probably the most conventional way to do it, just because then we're losing that DFA structure. We could just determinize at the end. Yeah, that is one way we can do it, but then in the process of determinizing it, we could then, it could then lead to a non-minimal automaton. So I'd probably just take a look and think about what 2 states we can merge, which will then not cause that sort of issue. Yeah. But yeah, that's what I wanted to cover in terms of minimal automata.